Hi there. So this is a recorded lecture to make up for an unavoidable absence. And we're going to continue on in a logical way from our week number 3 lecture. So first I'm just going to do a quick review of what we covered, as we usually do at the start of class. So last week we reviewed the perfect wall, this partie diagram that you've seen an awful lot of. And last week we did spend some time looking into the support function in quite a bit of detail. And now we're going to start doing one of the control layers, the most important one, which is rain control, water control today. And then subsequently we're going to do air, thermal, and then do some finish work. Now, so just to review here, the support function of the building enclosure is job number 0, as I described it, saying that if we don't get, we need a support so that we can do the other stuff. And these support layers collect, resist, and transfer mechanical forces to the superstructure or the foundation, but they are sometimes commingled with the superstructure. This is perfectly the case with low-rise wood frame buildings. But for many commercial, high-rise, modern building systems, we have a separate superstructure and a separate enclosure structure. And the examples we looked at last class were concrete masonry units, or solid concrete adobe could be a support structure, and they are also the type of system that might also be a superstructure for a lower mid-rise building. Light gauge steel framing can be used as a part of the superstructure, but is very much 90% used as a support structure only, meaning it doesn't support the floors or the roof or anything like that. Wood framing, light wood framing, is very much, again, 90% of it is used in the superstructure and support structure role on lower rise buildings, but we're starting to see it be used more and more as infill, meaning pure support structure, no superstructure. And then I mentioned aluminum tubes as being quite important to understand as being a support structure, which is what we use for a lot of curtain walls and window walls and so on. So that was the support side. And I tried to emphasize this idea that you needed to manage movement between the two. There's a difference between the stiffness and hence the amount of deformation that occurs between the superstructure and the enclosure support. This is something that we really need to do when we're designing, is to make sure that we provide flexible joints between the superstructure and the enclosure. But we also can use this fact to be able to identify in a drawing, well, is this the support or the superstructure? Well, if there's a movement joint between, then you know that there's a superstructure and support structure being handled differently. So this is definitely something that it's a normal practice, and it would be a pretty big mistake not to include movement joints between support structures such as curtain walls or steel studs or non-gravity bearing CMUs or precast concrete or etc. Now, when we look at the gray lines that form the support layer in the perfect wall, those can be given dimension by knowing something about the structural support requirements. And so when it comes to the support layer, we're basically talking what's the distance required to span from floor to floor if it's a wall, or from joist to joist if it's an open web steel joist system in a roof. And you find out the span to depth ratios that work for those types of systems by reading the document that's been provided on Learn. Now, we're going to dive in now into the control layers side, and control layers are needed to fulfill the primary function of the building enclosure, which is to separate the exterior environment from the interior environment. And that function generates loads because of differences in heat, air, moisture, fire, sound. And to control those forces, we create these components, functional components, called control layers. Now, although they're a functional component and they can be a physical layer, so that functional layer of water control can be manifested in design as an actual layer, where it's also quite common that we have air control and water control rolled into one material, or just as much that, say, something like thermal control could be provided by many layers that physically exist in the assembly. But when we're trying to analyze and design at a higher level, we're trying to define things functionally. So the function of rain control, or water control more generally, is very important. It's kind of job number one. It's the thing that's been challenged of our buildings, and yet it is one of the more fundamental requirements of our building enclosures. And just as an example, this is a quote from 1485 from Leon Alberti Battista, who wrote the 4 books of architecture, which were loosely cribbed from the 10 books of architecture by Vitruvius. And just pointing out that this has long been seen, rain control has long been seen as a challenge, as a concern. Also, you'll notice the photograph here on the right-hand side is an example of a rain test. We're testing claddings, 2 different types of claddings with a window in them, the water's flowing over them. And this is one of the kinds of testing things we would do with new ideas, new systems, to evaluate whether they will meet the performance expectation. Unlike things like structure and even heat flow control, though, it's really hard to predict rain control performance or just test it. And so a lot of this has to be done by understanding the philosophy that you apply to design and specification and construction. And so that's a lot of what we're going to do in the next hour or so, is talk about how we approach rain control, rain penetration control in enclosures, particularly enclosure walls. Why is rain so important? Well, on one level, it's easy to say that rain is the largest quantity of moisture that can influence the building enclosure. So on that level, it's obviously important. But it's actually more than that. It's actually hard to predict and handle rain in the quantities that we get. It's also a changing target. Today we need much better rain control than we did 25, and certainly better than we needed 75 years ago. And that's because we've improved the insulation and air tightness of our enclosures. So why is there a connection to rain control? Well, one of the parts of rain control that allows us to tolerate very small leaks and errors is that wall assemblies, roof assemblies, even basement walls have the ability to dry small amounts of water and therefore leave the enclosure harmless. As we've added air tightness and insulation, our ability to tolerate small leaks has gone down. Also, we're starting to make our assemblies out of much more susceptible materials. We're trying to take materials such as a concrete block wall with a brick face and replace it with a light gauge steel stud, gypsum sheathing, and a light metal cladding or something like that. Well, the difference in moisture tolerance of those two systems is vast. The amount of water leaks and mistakes and errors that can be tolerated by the brick and block system might be 100 times, but it's certainly 10 times more than the light gauge steel with exterior gypsum and a light metal cladding system. So those changes have meant that rain penetration control is harder because we must meet a higher standard in our systems. And we're not going back because we're trying to save resources, material, and the environmental impact. Now we're going to start dealing with rain penetration control and enclosure walls by looking at site and surface, site and massing, which deals with exposure. Then we're going to look at surface features. And then finally, we're going to look at the actual enclosure design itself. And we're going to do that with the help of a mnemonic called the 3Ds. The 3Ds was a concept that came out of the problems that were experienced in Vancouver, British Columbia in the very early 2000s. The concept that rain control was a kind of a multi-stage approach had been developing for quite some time. But this nicely sums it up. The first D is deflection. And what that tries to encompass is the things that reduce the amount of rainwater on the wall. Things include trees, include the location of the building on the site. Are we putting it on a hilltop or in a valley? Are there buildings around it that protect it? Or is this a very tall building that sticks up and is exposed? So those are the kinds of things that are considered exposure. And the difference in rain exposure between a highly exposed high-rise building that is well above any geographical sheltering of elements and that of a, let's say, a one-story bungalow surrounded by fully grown trees in a subdivision will be, again, a factor of rain deposition that might vary by 10 or 30 times. So it really changes things. Now, once the rainwater's on the building, there are still things that the form and massing of the building can do to help. And that has to do with steeply sloping surfaces, drip edges, and shedding. So that's all under the deflection category. And we're going to look at that next. There's also what we do with the enclosure. That's the drainage, exclusion, and storage. Now, back in the 2000s, they focused on drainage, but there are two other very important ways or strategies that we use in enclosure design to deal with rain penetration. So we're going to look at those three next. And then finally, there's the drying side. As I'd mentioned, we can tolerate a smaller amount of built-in moisture, small amount of condensation, and a small amount of rain leakage because materials can store moisture and then they can dry it out. And if they dry it out soon enough, no problem. And so consideration of drying becomes important. And that's the third D of the 3Ds. So the first of the 3Ds is deflection. And these are all factors that affect wind-driven rain deposition on building enclosures. Clearly, this is a pretty important factor for walls, but not so important for roofs. Now, the things that we look at are things like the site and whether there are trees that are large near the building, taller than the building. Are there other buildings the same height around or taller buildings around? And then we have things like the shape of the building. We'll be looking at things like pitched roofs and overhangs. And then we move closer to the building and we start thinking about surface features like drip edges and projections and cornices. And of course, at the bottom of the wall, we also think, does the ground slope away from the building or towards the building? These have obvious impacts on how much water the building enclosure needs to deal with. Now, before we just drill down into the actual building or even the particular narrow site definition, the location on the planet depends. That's a climatic effect. And then we move to exposure. And that means, is it a tall building in a city? Is it a short building in the country? Or is it a tall building in the country? The wind speed directly relates to rain deposition, but not just your average wind speed. It is the local wind speed. And so what that means is that the wind speed at 3 meters or 10 feet above grade is slower than it is at 30 meters or 100 feet above grade. And that increase in speed directly impacts the amount of water that will be driven against a building facade. So understanding the distribution of wind speed as you climb upward from near grade to the top of the building matters. And this can be assessed quite precisely, actually, using wind engineering standards. Now, they're usually doing the analysis for very high wind speeds, but it turns out that you can use the same knowledge that has been developed for the more typical wind speeds that occur during rainstorms. And as you can see from the image on the bottom left here, I'm focusing on, in a highly built up urban area, actually the wind speed grows more slowly with height because there's so much obstructions in the way. Whereas if you're on the edge of the ocean, or you're on on a lake or across a prairie, there's very little to slow the wind down. And so even at a 2-story height, the wind speeds are pretty high. Another factor that becomes closer to the site is things like, are we locating the building on let's say, a top of a hill or an escarpment? And the wind engineering allows us in the upper right to calculate the effect of how much the wind speeds up relative to the normal expectation when we look at things like a hill in the top right, or in the bottom right, that happens to be called an escarpment, where it's just a quick jump up, or a cliff is the extreme. And again, we can calculate using the National Building Code of Canada Part 4 commentary, or the ASCE 7 in the United States wind standards, which give you pretty much the same answer. So these effects on wind speed are directly correlated with the amount of wind-driven rain that can occur. Now, the building shape, or massing, if you will, also matters, depending on whether the wind is going up and over or around the building. When the wind is moving, it is taking raindrops with it. And, of course, big raindrops can't turn corners quickly because they have momentum, versus small drops, which can. And so this is a bit more complicated, a bit harder to predict, although significant progress has been made in the last 25 years to at least give us as much quantitative and qualitative information as one normally needs when you're selecting building enclosures. So this is an image of a building in Kitchener-Waterloo. Happens to be usefully cuboidal in shape, happens to be usefully made out of precast concrete. So we can see, after several hours of rain, what the deposition looks like. And obviously the wind having to go up and around means that the top of the building gets a lot of water and the edges get a lot of water. And as you move down the facade, you get less and less, and it's mostly at the corners. Now, what's also interesting is that this building isn't, like most buildings, isn't a perfect cube. And you can see that the central area of the building, by the atrium, I guess I would call that, would be somewhat sheltered. So if I'm going to mark this here in red, and if you look at the actual area, that's actually recessed about 2 meters, almost 2 meters, 1.5 meters. That's completely dry, even though up here is really wet. Similarly, you can notice down here, we're actually getting what looks like water staining from dropping some straight above onto that building. So it's just going onto that projection down below. Important other features you can tell from the staining is that there's rundown going on. So the concrete at the top here is actually getting quite wet, and therefore it's saturated and it begins to run down. The windows, of course, they don't get saturated. They don't absorb any water at all. And so the water will run off. But also importantly, the window sills, which you can see better in these lower buildings, are actually just a steep slope that takes the water and dumps it onto these panels. And you can see the joints are not having as much water, and that's likely from the shape of the joint. But when you look really closely, will be something that redirects water to certain directions. So there's lots that can be learned by just keeping a keen eye out at the beginning of rainstorms and looking at how different kinds of building features affect rain deposition and runoff. I've sort of tried to simplify, summarize some of these concepts here on the diagram. On the left, this is where we expect rainwater to be deposited, the darker blue at the top and the edges. And then we expect it to begin running down. How soon it runs down depends on the cladding system. But we definitely expect under the windows here, that's where we expect the rundown to show up first. And what may not be obvious is that there is deposition here on the sides of the building. And that's as the wind swirls around the top. Some of the wind will carry droplets and actually wet the side of the building at the top. So the top of the building gets really hammered, and that's where a lot more robustness is needed in materials, in design, in construction, in maintenance. Other thing to notice here is the splashback at the bottom. As water falls off the building, is shed off the building, it'll hit the ground, and in many cases that means it'll splash back depending on how the ground is treated. So here's a couple of example buildings of the sort of long, not tall, but wide building. So you can see that all the rain is being deposited at the top in this building. And you'll also notice that there's some distinct drainage runoff coming from the windows, right? Not a lot of water is hitting the walls, the masonry walls next to it, but it's being absorbed, that small amount. In the windows, that small amount will not be absorbed, and so it runs down, and depending on the design of the windowsills, not great in this case, we see water dribbling onto the wall below. The bottom right building is just interesting to say that if you look at the left or the right of the central entrance, it's actually not a lot of water being deposited. Even so, that little bit of water is resulting in rundown over the windows, which is accentuated by the metal panels that are above the windows, which also don't store water. But what's really stands out is the fact that this parapet here, the triangular parapet, sticks out into the wind, and in fact they even have a hole in it to encourage wind to go through, and that just concentrates rainwater that would normally be going up and over the building and landing on the roof, and now it's being saturating, and you can see that this parapet is going to be exposed to some pretty extreme, or much higher, let's call it that, much higher rain deposition than the rest of the building. Provided that the materials are appropriate, maintenance, construction, quality control, all that, that's okay. But as a designer, as a selector, as a builder, or as an inspector, these are things you need to know about to understand where to put your attention and why you would make different choices or change things. An important and often overlooked, I mean, before I would say 2000, modern design, even in the building science world, didn't really talk much about pitched roofs and overhangs as a rain influencer. And there's been a lot of research in the last 20 years to investigate this. And I would say by now we have some really good confidence that we know that they can make an important difference. And this is not because of any kind of shadowing effect. It is like the sun is shadowed with straight lines from the sun. This is all about redirecting the wind around a building in a way that raindrops are not deposited on the walls as much as if there were no overhang or pitched roof. So while I can show you a lot of measurements, even measurements I've done on buildings, it's actually easier to see more of a summary of these results by looking at these trajectories produced in Belgium from a computational fluid dynamics study, a computer modeling study that was compared to a test hut that had both a low slope roof, as you see in the bottom, and a pitched roof, as you see on the top. And obviously, you can see there's light rain is described as a 0.5 millimeter drop. Well, as rainfall picks up, the droplets get bigger. And as the droplets get bigger, they have more momentum. So it turns out that, a typical rain might be around a 1 millimeter average droplet, but there's a distribution, obviously. Heavy downbursts are 3 millimeter drops. And then on the lighter rain side, but still rain, not drizzle, we have the point fill at 5 millimeter. And if we just focus, say, more on the 1 millimeter average, it's raining, you definitely are putting your hood up before you go out the door, etc. With a 5 meter per second wind speed, you can see that the wind is being distributed away from the building such that the raindrop trajectories actually deposit their water in front of the building, not on the walls. Now, the roof still gets wet, you can see, but the walls are highly protected by this steep roof and the modest overhang. If you look at the roof that has actually a relatively steep slope for our considerations, normally we look at 1 or 2%. This is a 5% slope roof with an overhang. You can see the water is being deposited on the walls. There's a little bit of a benefit, but mostly the rain that is approaching the building is being deposited on the walls. And that's just switching from a steeply pitched roof to an essentially low slope or almost flat roof. So we also know that overhangs, and they didn't do this study without the overhangs, but we can show other studies that have. Also studies in Canada where buildings have been researched with movable overhangs to see the effect. And this is a study from the early 2000s by RDH. And it was started by Morrison Hershfield. These are two big names in the building science world. And they were analyzing 45 or so buildings that had rain penetration failures in Vancouver at the time that the condo crisis was developing. And this was an analysis when they took the data and they then broke it down to say what percentage of the walls that they looked at had a problem as a function of the size of the overhang. And you can see it was a pretty strong correlation that no overhang, 90% of them had a problem. But at 24 inches or more, which is 600 millimeters plus of overhang, we still had 25% had problems. Now that could be partly because, for example, those overhangs still had balconies that projected out 5 or 6 feet that collected water and brought problems in. And also there were other related problems with the buildings, such as air leakage, condensation, and movement, cracking, and so on. So that's why you can't eliminate the rain with over 24 inches. Historically, we've seen an awful lot of overhangs. In fact, it's only in really dry desert type areas that there is not some effort made to have an overhang. And these are 4 buildings from around the world. And not all of them are particularly rainy, although they all have moderate to higher rainfall rates. And they're all older buildings. The newest one here is the bottom right, which is a courthouse in New Zealand, made with wood siding, but with really, these 24-inch type overhangs, quite aggressive, especially for a 1 or 1.5 story building. And that's why this building can survive 120 years in a rainy climate, being made of wood. Now, the Forbidden City here in the upper left is actually quite a bit older, and you'll see that it has multiple roofs, as you would, as a way of shedding the water off the building. It protects this wall with the overhang above, but these are wooden, beautifully made wooden carvings and paintings, etc., and they are under an overhang that measures in the several meters range, as you can see here. Also, the building is raised up on a podium so that the water drains away. And you can see here in southern Germany, they're doing the same thing. This is a place where it rains almost as much as, say, a place like Vancouver, not as much as, say, Halifax. But the ground is sloping away. This is a masonry building, but it uses wood If you look here, these are wood roofs and wood balconies. And the overhangs, again, are measured in the meter, sort of a meter and a half, even 2 meters dimension, which means that the walls just almost never get wet. So it allows you to use a much less durable building material, or much less robust detailing, or much less skilled trades. You got all those options or some combination. And this is just another example from Lake Baikal in Russia area, and this is a traditional way of building their houses out of wood with lots of ornate details that act to shelter, to deflect wind-driven rain so that it doesn't cause a problem. Now, this type of approach is not just applied to European wooden buildings, but this is actually in Canada, in Toronto, and you can see that there is a very nicely steep slope here. We have an overhang there, and another cornice here, and another cornice here, and another cornice here. And these cornices are acting like overhangs on a high-rise building. So they mean that they can provide sheltering effect at multiple levels. Now we're going to start moving into more of the surface details, though. See, this masonry has metal on top to deal with the higher rain exposure. The steep roof would be slate because that's a durable material that can get wet a lot in our climate. The window sills have nice steep slopes. You can see here on the bottom that where you can see the slope is more visible. The heads of the windows all have detailing around them. And if you look on the side section here, it's just to show that, by doing those heads, we're shedding the water away. We're redirecting the water to the side and protecting the more sensitive parts of the building. It's somewhat ironic to me that many of these details exist in buildings that have really thick walls made out of highly durable and moisture-tolerant materials like masonry, and then we don't use them when we build buildings that are made out of light-gauge steel stud or fast-growing plantation wood framing. So here you see on the upper left, building from Pennsylvania, very large head flashings or head details, eyebrows directing water out. National Cathedral here in Washington, D.C. So not as old as Europe, but following some of the traditions of Europe where water is directed down and then shed off the face of the building. Steeply sloping windowsills. This is not a place where rainwater sits, and so that it can find any kind of crack and opening to get into. It's shed off the building as quickly as possible. And on in the middle here, you can see this is a building happens to be in Kansas, where pre-made window sills with recessed gaps to make sure that when you mortar these pieces together, the most sensitive bit, the mortar joint, is kept up out of the water, so that water that runs off is encouraged immediately to run into this and then out and away. Now, with windowsills, or parapets on roof, coping on a roof parapet, or any kind of horizontal surface that then intersects with the wall, we are working also on shedding the water. It's not just at the eyebrow of a window. We use metal, as shown here in this left-hand side example, and often what's called hem the edge, H-E-M. It's like hemming a pair of pants. And that hemmed edge is to stiffen the edge to make it safer, not so sharp, but also stronger. But it also provides a spot for water to drip off. And that dimension is, we want it to be more than half an inch, and more likely like something like 25 millimeters would be good. And that ideally should be shown on drawings to make sure that there's no surprise that we're expecting the windowsill to collect the water and shed it off. On the bottom right, you can see that we have a masonry version, And rather than bending the metal, we make a saw cut or kerf, K-E-R-F, in the stone or concrete. This can be cast into concrete or cut into concrete or stone, but it's making sure that water droplets reach an interruption and then drip free. This here is an example of a German windowsill, and it's a precast concrete wall below, but notice the projection here, the amount that this sill is projecting away from the face, and also notice the end dams or the side dams that stop water from running off the edge. So that you're not allowing that to happen. Often missed, and it's actually challenging because right here at this corner right here is where a lot of water will be pushed by, say, the blowing wind. It'll either be this side or it'll be this side. And so here they have this upturn side or back dam, end dam, sorry. This is a back dam right here. This is at the back, and that's make sure that the water flows this way. This is a end of the sill or side of the sill, and that makes sure the water flows this way. What was done in the past for masonry, they had other options available. And you can see this is what's called a lugged sill, which means that the sill is actually inserted past the jamb of the window. This is the line of the jamb of the window, and almost you really should try hard to make sure that the windowsill extends past that so that water can't run around the edge. But this lugged sill takes it to a whole other level in that by putting in these, chiseling into the granite that is this windowsill, these grooves, which is how you shape granite with a stonemason's chisel anyway. It's just normally they then smooth it off. And in this case, they left them exposed, and that really directs water to follow along that texture. There would take quite a bit of wind to even make it go a little bit to the side because of these grooves holding the water. So I just find it interesting how when you look at these older buildings, you can see that there's some really clever solutions and also a direct concern with how do we manage water on the surface. This is, of course, some of you may recognize, this is a building in Cambridge, Ontario, just across the river from the School of Architecture. And these are terracotta tiles that were used to form the building enclosure here. And again, like the building in Kansas, you see how much effort has been put into shaping these not to be a flat unit, but to raise the moisture sensitive and leak prone joints in mortar up out of the water. And so the vast majority of the water, a beautiful slope downward and highly protective of the joints. And then the water is also, it reaches here and there is a drip to protect the wall below. Very useful and correct design. I don't want you to think that we never do this in modern buildings. We absolutely do. But it's also often not thought about enough and not given enough concern. And so here's an example from a tract-built house in Waterloo, Ontario. You can see that the saw kerf is very clearly cut. The dimension of the projecting lip is of European standards, like it's got to be well over 25 millimeters, maybe 35 millimeters. It is a lugged sill, the way to ensure that water can't run around the edge. So there's this dimension here is probably in the order of 2.5 inches or 65 millimeters. And that means that water has enough time to run over the front edge rather than making an end run and dripping uncontrolled down here. This is a building in Germany where they're using a granite sill. It's not quite as steeply sloped as I'd like it, but why I want to show you it is that rather than having the end dams raised up, they use the kerf approach, the saw kerf approach, cutting a groove in the granite to make sure that water running here actually is intercepted and then drips off here. And of course, there's also a saw curve on the bottom. So there's other ways of doing these things. The key is to think through how water flows on the surface and how textures, materials, and geometry can be used to guide that water in the least impactful way possible. As a little bit of a case study here, I'll point to the the New Zealand version of Vancouver's leaky condo saga. So shortly after we had the problems in Vancouver, and that would be, we started being aware of them in 97, 98, and they were really well understood by the early 2000s. They started to see similar problems in the early 2000s in New Zealand, which culminated with a full-blown crisis by the middle of that decade. And so I happened to be visiting New Zealand in response to this type of crises in 2003, and I've come back in several other times, but 2005. And this here are some images I took. And a number of people took me around to show me some of the problem buildings. And I'm standing in the parking lot when I take this picture here on the right-hand side, this picture right here. I'm standing here in the parking lot. I've literally gotten out of the car, and I right away take a picture, and I'm saying to my guests, my hosts, I'm their guest, about, well, I look at this building and I see nothing but risk for rain penetration problems. So first of all, we don't have an overhang, and we don't have a steeply pitched roof, right? That's right away raises the risk factor. The building's 3 stories high now. It's being pushed above the level of the surrounding trees and buildings, more exposed. But there are also some pretty interesting details. You'll see that is hiding a pitched roof in the backdrop there. That's pitched, and the water is running internally into a gutter, and then it has to come out. If you look here on the drawing on the left, it has to come out of what's a rain, it's called a scupper, but that scupper dumps its water directly onto this unheated wall system. And that projecting wall is basically a flat top. It's dumping all the rain from this roof area, and however deep the building is, on top of it. Any water that gets in will not have the benefit of accelerated drying by heat loss from the indoors, because it's outdoors on 3 sides. So there's just a whole litany of things that, when you think about rain deposition, deflection aspects, and you think about surface features, this building just does all kinds of things the opposite direction. Here's a deck. There's another scupper that penetrates all the rainwater collect on the deck, has to go through the wall in a perfectly leak-proof manner, highly risky. And yet, with all those risk factors, these types of buildings are being built out of the same materials, in the same assemblies, by the same trades as this house over here, which I've labeled difference. And first of all, pitched roof. Secondly, low rise, only 1 story high. Third, look at the size of that overhang. All the roof drainage is actually led into gutters or eaves troughs and downspouts that are on the outside of the building. So no chance of concentrated rainwater running through a wall. And so, and now, of course, I also happen to like the nice steeply sloping yard. Everything is being done correctly on the upper left to reduce the amount of wind-driven rain. And so the materials and the techniques and the assemblies and the trade quality inspection were all sufficient to build buildings like that upper left one with no problems. When they change the building form, massing, and features like they did on the right one, then we end up with disaster. Now, if you want to build a building like the one on the right, you now need to change your assemblies, your materials, your inspection, quality control, etc., or you should expect problems. I don't want to say that this is something unique to New Zealand. It happens all over the world with modern buildings that are designed without due consideration for deflection, the first of the 3Ds. So here we have a building in Western Canada where you have the slope here. They didn't hide it with a bit of a parapet, but instead they stuck a chimney right in the middle where all the rain would run. And so they had to come up with very complex piping and flashing to direct the rain, and happens to be snow as well, around, which is just begging for failure. Possible, but way high level stuff. And then you'll notice here that, oh, I wonder if this low slope flat chunk that sticks out, notice how much overhang? Well, maybe about 1.5 inches here and exactly 0 inches here. And so rainwater is going to be plastering up here because it's going to be deposited heavily, run down to this projecting bay window, which is not pitched, does not have a drip edge. And so, yes, the building is starting to show that bad things are happening inside. I can also, again, I'm standing again in the parking lot, a bit further from my car this time, about 20 meters from entering this, the entry of this 3.5-story building, and looking up and seeing all of the problems that when we disassemble this building, we're going to have to replace rotting framing, etc., sheathing that's gone bad, and so on and so forth. These are just challenging forms that require higher performance systems. This here you'll see, again, I'm going to go back to older buildings. A lot of times you'll go on tours and they'll talk about how these gargoyles were there to scare away the bad spirits, which is a good story. But really the majority of them actually are there exactly for rainwater shedding. They are the way that they hid rainwater leaders and downspouts and made them durably. You can actually even see there's actually a copper pipe that's being used to make the tongue of that gargoyle. This one is a bit more modernist. It's actually in Munich, and it was a building built early 1800s, and they were starting to explore more functional details. And the functional detail had this projecting spout to take the water off of the little terrace over there. But they didn't turn it into a beautiful gargoyle or a laughable gargoyle or a scary gargoyle. Now, I'm looking at the surface features. Now I want to say, let's take a look at the bottom of the building. All the water that is deposited on the wall that might be shed off. What happens when it gets to the bottom of the building? And here on the upper left, you can see the University Shops Plaza. We have a pitched roof which dumps water into this eaves trough, but the eaves trough is on quite a steep slope, which means that during heavy rains, the water just runs down here, goes past the downspout because there's momentum, and jumps over and causes this wood fascia to rot. And so the response is that they repaint that every 3 to 4 years and then replace the wood every 10 years until they finally have covered it up with vinyl siding over building paper. And I'm not sure if that's solving the rot or hiding the rot that's going on behind for a longer period of time. Also, you'll notice here, even though the roof is exactly symmetrical, they've just chosen not to put an eaves trough, and the water just drools over the edge. And in all cases, you can see the lack of overhang and water management means the base of wall is getting wet from splash and wicking up water from the asphalt parking lot. In the middle, I'll point out that we have this is from the Forbidden City again in Beijing. These are wood columns sitting on a carefully carved stone paver, which has an upturn of about 30-some millimeters. And that's obviously, it keeps the bottom of that wood column away from standing water. And I'll remind you, this is under a 2-meter plus overhang, which already does a big job of protecting this entire part of the building from getting wet. On the right-hand side, we have something like a 100-and-some-year-old shed/barn in Waterloo. And what we see is that the wood siding comes down really close to grade, and as a result, it's been rotting and slowly moving back again. And you can see that here by the door as well. And so it's in the building code, in the part 9, it specifically says you have to keep your cladding a minimum of 6 inches or 150 millimeters above grade. And this is just an example of why, is that's a good rule of thumb to protect most claddings from getting damage from water that's at the surface or splashing or melt water, which will, of course, over time degrade most systems. So all of those previous issues about deflection, rain deposition and exposure, height, surface features, etc. What we're doing is trying to get a better handle on how much rainwater hits the wall. Does it happen? Is it 10 kilograms per square meter per year or 100 kilograms per square meter per year? The difference in the amount of water that strikes a wall in particular, not so much roofs, but a wall, easily varies by a factor of 10 in the same climate zone, depending on normal deflection features like overhangs and surface features, etc. So that's why we spend time looking at this, is to understand how much effort do we have to put into controlling this.